everyone, welcome to class today. First thing we want you to do is in your packet, take out, open to the page that says probability warm-up. And we want you to do the whole entire sheet, but specifically put the answers to number 4 and number 9 on your blue sheet. Pause here while you do that and put the 2 answers on the blue sheet, and then you can unpause to see the answers. All right, here are the answers to the whole sheet. So I'll just scroll down so you can see them all. I'm specifically going to look at number 4 and number 9, like I said. So number 4 says prefers the NCAA and football, and is the overlap in this case, where they overlap. So we have NCAA and football overlap here, and then we have it out of 210. Because it says what's probably a randomly selected student, that's when we're going to divide by 210. For number 9, so that's why, by the way, that's why all 2 through 8 are all over 210. And then for number 9 and 10, it says who prefer NCAA, so that's why we're dividing by 95. And then so number 9 is 5, so NCAA, we want to see where NCAA and football overlap. But then this time we want to divide it by 95. So 5 over 95. Number 4. So those were those 2 answers we wanted to talk about, and then we will move on. We actually want to move on to another page from your packet, just talking about some Venn diagrams. And so we're going to do this problem together. So if you'll find this page, it should be 2 pages later, and we're going to do this problem together. So at a certain university, 38% of its student body eats at the school cafeteria, 78% at the food court, and 18% at both. So A is going to be the cafeteria, and B is the food court. So draw a Venn diagram to model the probabilities. So first thing you want to do for a Venn diagram is you draw a box. And then you make a circle for each of the events. We have one event A and one event B. So this is a probability model. So the probabilities in it should all be between 0 and 1 and add up to 100% or 1. So the first thing you always do is the both. And I like to put them in as decimals. So we have 0.18. That way it meets that criteria being between 0 and 1. A percent is correct as well, but I don't like to draw the percent sign. And so that represents where A and B overlap. And so we put that in the middle first. And then we look at A, where it says 38% of the student body eat in the cafeteria. So that includes the 18% that's already in the middle. And so what you want to put in this space out here is 20 or 0.2, because total this should add to 38 right here. We'll do the same thing with the food court. We're 78%. That includes the 18, so we're going to put 60 out here. And this time we're looking at we're looking at the food court. 78%, so this whole thing adds to 0.78 or 78%. So make sure you always subtract the middle before you put it on the outside, or else you'll be double counting it. And then last but not least, like I said, we do have a probability model here. So all the probabilities are between 0 and 1, and they should add up to 1. So right now, if I add them up, I get 0.2, 0.18, and 0.6. That adds up to 0.98. So I have 2% left over that we'll put in the outside. That percent of students eat at neither. All right, part 2 says make a two-way table from the Venn diagram. So a two-way table is very similar. We have food court, which we're going to use we have cafeteria as A and food court as B. And so that's what we want to overlap, A and B. Again, we know that 18% eats at both. Then if you don't eat at the food court or the cafeteria, we would use the little symbol B and A, C. Remember, the C means not, like a complement. And then we can also have a total. We could just use the Venn diagram to fill this in, but I also want to show you how we could use the whole problem in the first place. So they told us 38% eat at the cafeteria. So this should be 38 down here. And 78% eat in the food court. So that 78 goes over there. And so that's where I'm getting, remember, these 0.2 and 0.6. The total should be 100%. So we know this is 0.22. This is 0.62. And then that makes this 0.02, just like we have. So what we want you to see is that in the Venn diagram, if I use some different colors here, we have 18 here. We have, I'll use purple, 0.6 here. Let's see, green, 0.2 here. And last but not least, I'll use one more color. How about this purple? 0.02 here. So a two-way table and a Venn diagram are really call them best friends because they have all the same numbers in them. Okay, so number 3, find the probability of P of A or B. In statistics, or is synonymous with any. So A or B would be food court or cafeteria or both. So we could just add up 0.2 plus 0.6 plus 0.18 and get 0.98. We'll talk about that a little bit later on in the lesson too. A and B is where they overlap, so we know that as 0.18. Now, I'm going to show you some notation for only in the cafeteria. Only in the cafeteria would be P of cafeteria and not the food court. Remember, that means and that means not. So cafeteria and not food court, or cafeteria was A. Oops, let me fix that. Cafeteria and not food court would be that 0.2, where you can use the Venn diagram or you can use a two-way table. Only the food court would be food court and not cafeteria. That's the 0.6. And then neither is going to be a little bit interesting to write. We're going to write neither means not in A and not in B. And that's the 0.02 we wrote before. And then a student who eats in the cafeteria also eats in the food court. We'll come back to these later. That's part of our lesson later. Okay, so that's just a little intro to Venn diagrams and some notation and stuff like that. We have some notes to finish up from last class. So if you could go ahead and get out turn it back one page and you'll be able to write the rest of these notes down. All we had to do was the general addition rule. All right, so remember this symbol means or. Oops. Uh-oh, find the right one. This symbol means or. And so to find the probability of A or B, this is the rule from your formula sheet. It's P of A plus P of B minus P of A and B. If we did that with the formula from the Venn diagram question, we will be doing 78%. Oops, I'll start with 38%. That's P of A. P of B was 78%, and then P of A and B was the 18% overlap. And that's where we get 98%. Two-way tables and Venn diagrams are BFFs. So what we want you to make sure you see is that you have all the same numbers represented in either one. And in a two-way table, the and is where they overlap. And so that's where we use that and symbol. So P of A and B is 1. P of A and not B is 2. P of not A and B is 3. And then neither P of not A and not B would be the last one, 4. All right. So that's just us finishing up the other day. I wanted to Kind of spread that out a little bit. And now we're going to move on to the mind games lesson. So coin toss and rock, paper, scissors. This one we're replacing from your packet, so just get that sheet out that we handed out last class. Now, mind games, you have to be able to do this with a group of people. So if you're watching this video and you're at home, then you'll just want to collect, fill in the class data from the next page. So I'll just zoom in so you can only see that. And then once you fill in that class data, then you're going to go ahead and answer 2 through 7. And then pause the video for you to answer 2 through 7, and then you'll unpause it so I can go over the answers. So here is the data. Go ahead and fill that in on your sheet. Pause the video, answer questions 2 through 7, and then unpause to get some of the debrief from this. All right, so to start off with number 2, first of all, we know we have a two-way table right here. This is a two-way table. So it's got 2 different variables that we're looking at, rock, paper, scissors, and coin toss. So suppose that we randomly chose a student from the class, find the following probabilities. Rock, paper, scissors win, rock, paper, scissors tie, or rock, paper, scissors win, and rock, paper, scissors win or tie. So in this, first we want to label these as mutually exclusive events. And mutually exclusive means they can't happen at the same time. So when you play rock, paper, scissors, you can't win and tie in one hand. So we have those 2 events are called mutually exclusive. And when we looked at win or tie right here, we just add the 2 together. So we have P of A or B equals P of A plus P of B. We were just able to add together, if this were A and this were B, our 2 probabilities. So you want to show your work every time. You want to do 11 over 30 plus 9 over 30, and that equals the 20 over 30. For number 3, if you look, coin toss lose and rock, paper, scissors lose. Those are not mutually exclusive. Because if you look in the table, coin toss lose and rock, paper, scissors lose. Those were both right here in the overlap. So that's where they overlap. And so we were able to say that's not mutually exclusive. When we get to, because they have an overlap in the table. When you look at number 3, this third part of number 3, coin toss lose or rock, paper, scissors lose, then we want to think about that formula we wrote down a few minutes ago. So coin toss lose would be all of this. Rock, paper, scissors lose would be all of this. So if I were to just right now add together 13 out of 30 plus 10 out of 30, then I would be counting this 2 out of 30 twice. So that's why we have that formula. So the final answer would be 23 minus 2, so 21 out of 30. And that's why we have that formula of P of A or B equals P of A plus P of B minus P of A and B. So here's A in this case, B, and so when we do the or this time, we have to use that formula. And there's a lot of other ways to do it, but what you just need to make sure is that you don't count that 2 out of 30 twice. Because that 2 belongs to the 13 and to the 10. And so we take it away when we're using the formula. You can figure it out other ways, but that's how that formula works. Remember, or means any. It doesn't mean we're excluding the both. It means that we counted it twice, so we have to take it out. Okay, moving right along to number 4, 5, and 6. So we had a fraction, a decimal, and a percent is what we were asking you to write down. And then when we look at 5 and 6, 4 was just a regular old probability question. What's the probability that we're able to win the coin toss? So we'll say coin toss win. But then 5 and 6 have something else. They say, given that the person selected one rock, paper, scissors, what's probably they're able to predict the coin toss or win the coin toss is what your sheet says. So for notation purposes, given means that we use this vertical line, and it means that we only want to look at people who won rock, paper, scissors. So we're only looking at this column. And so that's why the denominator is 11. Same thing with number 6. It says, given that the person did not win, so this time we're only looking at the did not win, which would be losing or tying. So these two. And so that's why the denominator for that was 19. These are called conditional probabilities. Which we learned that word in Unit 1, and it just means that it's based on a condition. In this case, the condition is that the person won or didn't win for each of the 2 questions. Notation-wise, we're going to write it like this. P of, and we'll say coin toss win, given that they win rock, paper, scissors. Or this one would be P of coin toss win, given that they did not win rock, paper, scissors. So we'll use that little C for did not. So whatever comes after that word given is what comes after the vertical line and the notation that we use. And then when you think about the answer, you just want to make sure you only look at that condition. So if winning rock, paper, scissors is a condition, only look at this column. If not winning rock, paper, scissors is the condition, then only look at these outcomes. And number 7 are the events independent. We'll talk more about that in a minute, but right now it does appear that winning rock, paper, scissors or not winning it did affect the percent of time people won the coin toss. The answers were slightly different from each other. And so we think that maybe they're not independent, but we will talk more about that in a few minutes. So flip your paper over, and now we want to consider the data for all seniors at Ardrey-Kell High School. So what we're going to do is pause here and answer the rest of the questions on this page, and then you can unpause to get the answers in the debrief. All right, so for number 8, find each of the following, write those fractions, a decimal and a percent. It starts off P of coin toss win, and that's just going to be coin toss win is just this. But it doesn't say given anything, so it'll be over 475. And that's why the answer is 60%. Show your work, everything. But then with letter B, it says P of coin toss win given. Remember that vertical line means given. That RPS win. And so in this case, we only want to look at RPS win as our for our probability. So we have 180 in the denominator, and then of those 180, 100 of them won the coin toss. And so that's the probability, 100 over 180. And so the vertical line means that that's the denominator we look at. So keep moving on. Number 8F, are they independent? It looks like the outcome of the coin toss affected, or the outcome of rock, paper, scissors affected the coin toss percentages. If you look at these, all these different outcomes for rock, paper, scissors change the probability of coin toss winning. We have 60, 56, 53, 78, 63, and so it appears that it affected it. Now with number 9, we fill in the table as if it were independent. So if you weren't sure how to do this, what you want to think about is start off with just what percent of people won the coin toss for this table that's blank. And you have 285 out of 475. That's 60% are winning the coin toss. And then 40% are losing the coin toss. So if we think that the coin toss has no effect, or the rock, paper, scissors has no effect on the coin toss, or vice versa, then those percentages should stay the same throughout the table. So to get that 108, what I did was I thought, what's 60% of 180? what's 40% of 180? And that got me the 108 and the 72 for those same numbers. And then we also want 60% of 115 for the tie and 40% of the 115. So that's where those numbers came from. And then when you do all this math for number 10, what you'll see is that the percents are all the same, because in this case, if they're independent, knowing the outcome of one event doesn't affect the other event. So in this case, rock, paper, scissors would be one event and coin toss winning would be the other event. And if you look, no matter what happened, win, lose, tie, no, don't win, they all remain the same probability or percent as just winning the coin toss in the first place. So that rock, paper, scissors game had no impact on the coin toss. So if we generalize a rule, we can let A, coin toss win, be A. And then if we look at, we can let rock, paper, scissors, like it says, winning be B. So that would be, this one would be P of A given B. And then not winning be A given not B. And so if the two events are independent mathematically, what should happen is that P of A should equal P of A given B, which should equal P of A given not B. All right, so using the rule in number 12 and the table below, determine if the event's first class passenger and survived are independent. So this data is from Titanic, and we want to, we've all heard or read about the Titanic and seen the movie where it's really sad that all these first class passengers are getting on the boats and everyone that wasn't first class wasn't that lucky. So we can use math to see that discrepancy. So if they're independent, then your class on the Titanic will not affect the rate of survival. And so we're going to look at the survival rate in general, then look at the survival rate from first class, and then look at the survival rate from not first class. So P of survived is 500 people survived out of about 1317. Then we can look at survived given first class. So out of all the first class passengers, there were 324 first class passengers, and 201 of them survived. And then everyone else would be, need to have a little math here. We're going to do 1317 minus 324. There's a total of 993 other passengers that aren't first class. And of those, 299 survived. So what we can see here, even if I'm not going to do the math in my calculator because we can see it already. Well, we should do it, but I can see here that less than a little bit more than a third of the passengers survived. So this one, I'm out of room, but this one equals 0.38. So a little bit more than a third. I can already tell 201 out of 324, that's close to 2/3. But I'll do the math. 201 out of 324, 62%. And then the other group, so that will be that's going to be way less than a third. 299 out of 993. Not way less, but 0.3. So the class that you were in affected your survival rate, because being from first class increased the survival rate from 38% to 62%. So we would say no, they are not independent. All right, so we'll put that all together in our notes on the back. It's not very long, so we'll just have a couple things to write down. First is conditional probability is the probability of A given B. And the way we write it is that vertical line is the given. And so we always will put P of B in the bottom. Whatever comes second goes in the denominator. And then the numerator would be where they overlap. So remember, that means and. I'm going to use those interchangeably. Independent events is when knowing one event has occurred does not affect the probability of the second event. And the way we'll check that rule is if P of A occurs, then looking at B or not B shouldn't make a difference. So you'll want to check that math to determine if they're independent. Here's a good chance for you to practice on this check your understanding. Went ahead and labeled what it said to use. They say E for environmental club, S for snowmobile owner, and N for never used. So you just want to kind of use those same letters so that your answers can be in line with the problem. I'm going to pause here. You're going to pause here. Try to check your understanding, and then you can come back to check the answers when you're ready. Pause. All right, here they are. Find P of N given E. So E is environmental club. That was this group. We want 305 to be the denominator, and then because we're looking at only 305, my numerator can be from only that column, so 212. Number 2, it says, given that the person is not a snowmobile owner, so we have that vertical line, whatever comes after the word given, so snowmobile owner, and then not, it means we use the C, and so not a snowmobile owner would be everyone but the owner, so we would look at only renters and never used, and then add those together and you get 1231, and then the numerator would be 289, not 212 and 77 added together. Are they independent? So you want to make sure, we just check the rule. P of E is P of E given S is P of E given SC, and you can do it, you could have done S and then S given E and then S given not E as well. That would have worked, but we already calculated this one. So that was the best one to use. Just try to be smart about it and use something you've already done so that you don't do too much work. Especially mostly for the AP exams, they'll want you to use something you've calculated already. All right, so pause here and check the rest of those answers. And that's about it. There should be a little homework assignment for you to do in Sapling. Email if you have any questions. I hope you guys have a great day.